समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. See people still joining in. There are about 26. I think usually the strength is 41. We'll just wait for the rest to join in. At the end of the class, just remind me to take another together mode photo so that the whole class is there. I think the last time we took it, probably half the class wasn't there. I'd like to have it as much a full audience as possible. There are 34 now. Probably we can get going. You able to see my slides now? Okay. So welcome to the 6th class, topic being continuing from where we left off. We were talking about various skeletal components. Now we are talking about the transverse members in a little more detail. Giving certain examples because I think there were quite a few questions as well related to the transverse members. So let's try to cover that a little bit. And then to the main crux of today's class, we'll go into the classification of these components from a structural engineer's point of view, which is more into beams, bars, shafts, and shells. And the quiz that I gave you, a quick quiz, was basically intended to do that, to set the stage for this component classification that we shall take up in detail today and probably in the coming classes. Then let's see if time permits, we'll talk a little bit about the material selection criteria, which might mostly go into the next week. So before that, I'll probably give you an assignment, the second assignment of this course. This assignment number 2 involves once again searching certain online resources. If you are able to access from the IISc library the Jane's All the World's Aircraft, that would probably be a useful resource. But if you're not able to do that, that's fine. Whatever online resources that you can lay your hands upon. Many of you using a VPN connection, which you can probably get through the computational CDS department, unless you have already obtained it, might be able to access the various resources from the library. So if you're able to do that, well and good. Otherwise, send an email to either Rajesh, Renuka, or Vignesh at this email address that they have created for the assignments as well, so that we can ensure we put you in touch with the right people to have those access, or change the settings which are necessary for you to be able to access the library resources from wherever you are. So this assignment involves finding at least 5 examples each of the 3 types of constructions that we have talked about for the we talked about for the fuselage as well, but let's focus this assignment just on the wing alone. So truss-like structures, like what the Wright brothers did and a few other aircraft after that as well. The monocoque constructions, as well as the semi-monocoque constructions, which are stiffened shells. We will just focus this assignment after you find about 5 examples of these kinds of aircraft. The rest of the assignment will be focused only on the monocoque and the semi-monocoque construction. For those examples that you have found from the literature or the online resources, you need to create a plot of the skin thickness versus the wingspan, just to see how the skin thickness changes with respect to the wingspan. So this will not be a continuous line or curve. It will be just points depicting those 5 monocoque and 5 semi-monocoque wing constructions, just dots on that XY plot, where on the x-axis you would have the skin thickness, on the y-axis you would have the wingspan, or vice versa. But basically you're trying to look at identifying certain clusters of these points. We would also do that for the skin thickness versus gross weight. For consistency, let's say in both cases, let's put the skin thickness in the vertical axis and the wingspan or the gross weight on the horizontal axis. Okay, 2 separate plots with about 10 points, or how many you are able to lay your hands on. Because as I've said in red over here, the skin thickness data is difficult to obtain, because this is kind of confidential information most aircraft manufacturers will not share, and this is also something which will change along the span of the aircraft, and probably even along the chord. So wherever you're able to get some related information, mention which location it is at, if that location is mentioned in the resource that you have. There is a saying that for anything that you need, you can beg, borrow, or steal. I'd like to just change that and say search, research, beg or borrow, but do not steal. So get this data, which is, I know, very difficult to get, but from whichever resource you can. Maybe your own classmates, some of them might be from HAL, ISRO, DRDO, NAL, who might have, or like your squadron leader, Franklin. So they might have a little more opportunity to find these resources. So befriend them and try to borrow from them as well. This is an opportunity for those of you to make friends, because it's much easier to make friends when you're all at the same hostel or attending classes together in a physical sense. But now that it's all online, I would like to create opportunities for you to interact with each other as well, not just with me and the teaching assistants, but with the rest of your class. I'm sure many of you would have probably already started doing that. I know some of you have created WhatsApp groups between yourselves and try to interact. These interactions are very important, healthy, in order to not only establish proper understanding of your classes, but also from a human point of view in terms of establishing better relationships. For example, I myself did my ME, which is what the current MTech was called, at the Aerospace department in IISc, like you, 92 to 94 batch. And I remain in touch with many of those students now, and they're all in many different positions around the world. But that camaraderie really helps, not only professionally, but also in terms of maintaining healthy human relationships. So this is something that you should try to do, go out of your way to do that. And this is an opportunity where if you don't obtain skin thickness data online, try to interact with your rest of your classmates and try to share the data, whoever is able to obtain that. This is more not a competitive assignment, it's more of a teamwork, because eventually all of you, even if you work in the aircraft industry, are not going to work as individuals. It's not possible, because especially if you're into the design, etc., you have to work in large teams. And the sharing of information between the team members right from the beginning is very, very critical in order to accomplish any major useful task. So that's something that I want you all to do. Try to get as much information as possible from amongst yourself. So this will be this will be an assignment which will be graded for the entire class as an average, rather than for you individually. So it will just help to anything that you contribute will contribute not only for yourself but for the rest of the class as well. So join together, try to access as much data as possible in the 1 week time that you have till next Thursday in order to get these plots in place. Skin thickness versus wingspan, skin thickness versus gross weight. Again, I repeat, these are not curves, but just points on these two plots. What is more important is the inferences that you draw from this data, whatever data set you're able to eventually collect. Comment on those clusters of points. You'll probably see that some points are coming close to a particular location. If necessary, you could even try to non-dimensionalize it in some way. You try to be innovative and try to see if clusters are not forming in this dimensional plot of skin thickness versus wingspan or skin thickness versus gross weight. Try to non-dimensionalize it in a certain way. Let's say you take the heaviest of those aircraft and then take it as a percentage of that, the remaining thing, or something like that. Try to come up with your own innovative ways to see how you can see certain clusters of points. So this will actually help you to see what is the trend. That is what is most important over here, to understand what is the trend that is there in terms of the skin thickness, how it changes with wingspan, how it changes with the gross weight. Because the wingspan is in essence a way of talking about the size of the aircraft in a length sense, in a dimensional sense, in a spatial sense. Whereas the gross weight is again an indication of the size of the aircraft, but more from a mass point of view. This is the maximum takeoff weight that we are talking about when I say gross weight over there, because there are various other things, the empty weight, etc. But what we are talking about is the maximum takeoff weight of that aircraft, whichever you choose. So then I would also like you to submit along with your whatever end result is there, the references that you have looked at, some soft copies of that, not the entire documents, just the relevant pages of that document or relevant paragraphs of that document, but mentioning very clearly what is the source. It could be the URL, or it could be a particular book or paper that you're referring through the library resource. Just mention that, because going forward, it's very important for you to cite whatever source that you get your information from. This is a healthy profession professional practice that should be encouraged right from the beginning, irrespective of whether you write journal articles, etc., later on as part of your research, or even your own thesis or dissertations that you're going to write. It's always a healthy practice to cite the sources from which you get your information. Is this clear, or do you have any doubts on this particular assignment?
Excuse me, sir.
Yeah.
This is Vignesh.
Yes, Vignesh.
I think if the people are in remote places and not in IAC, they can connect to IAC network through VPN and then have access to the journals. I checked actually the form that you had sent. Many of the resources are available as Springer resources and as ebooks, which are in downloadable format. And I also think they know how to acquire resources without getting through to the library. If students have any issue in acquiring resources, they should let us know.
Sure. Yeah. Thank you, Vignesh. I think that will really help the students, some of them who probably are not yet aware of it. So whoever is not yet aware of how to access either the IISc library or some of these resources, please get in touch with this email address, ae204ace@iisc.ac.in, and either Vignesh or one of the other two students will respond to you so that you are able to access them. Anybody else? Anything that you want to know about this assignment?
Sir, I'm Harshil here.
Yes.
Sir, just I want to confirm that there will be 10 points on each graph, which will be 5 of monocoque and 5 of semi-monocoque.
I don't think I heard the full question because there was some noise at the background. Can you just repeat that, please?
I'm telling that there will be 10 points on each plot, which will be 5 monocoque and 5 for semi-monocoque.
That's correct.
And that 10 points are which we have taken example above.
That's correct.
We can't take different aircraft other than example.
You can take more. I mean, that is the minimum that I'm asking for. At least 5 is what I have said there. At least 5 examples of each. So try to get that. If you are able to get more, well and good. That's nice. And as I said, this is a teamwork. You're doing this as a whole class. Okay, so there's one submission that is going to be there for the entire class. So share that information over whatever groups that you are in. You could do that even on the Teams chat. So you have that Teams chat where you can communicate with each other, or through your WhatsApp groups or whatever. But basically at the end of the day, you are going to submit just one for the entire class. So pour in whatever information that each of you are able to gather in. Some of you might just be duplicating each other's information. That's fine. But it might be from a different resource, so you actually get a reconfirmation. So put it all together, and then you would have a minimum of 10 points for the first plot, and a minimum of 10 points on the second plot. That's all that matters. But more important than these is the what I have listed as point 4, that is to comment on those clusters. Why you think it's happening that way, and is there some kind of a trend, and if there is why, if there is none, why not? So I just want you to completely go with an open mind and see what's really happening, because this is something that will help you understand distinguishing between monocoque and semi-monocoque on the one hand, and looking at the trend as the aircraft becomes larger, either in size or in weight, what is typically required from a thickness point of view, and then whether that change is happening from a monocoque to a semi-monocoque like what we discussed in the class or not. So many different aspects that you can draw inferences on. But the most important thing that I want through this exercise is that team bonding between all of you, so that going forward also there will be a few such team exercises, so that you're able to understand that what you can achieve, each of you as individuals, even if you put together, will not be as great as what you can achieve as a team. So that's the thing that I want to bring out of this particular simple exercise. Anybody
So,
else?
sir, there will be different thickness for fuselage and wing. So means
Yeah. So this is not about fuselage. It's only wing. Okay. So we are only talking about wing over here. Okay.
Sir, the gross weight will be aircraft gross weight.
Yeah, that's correct. So maximum takeoff weight of the aircraft. See, the weight of the wing is a part of that, which we are not concerned about in this particular assignment, but they're kind of related because see, the weight has to be balanced by the lift, which has to be almost entirely provided by the wing. So the sizing of the wing depends not on the weight of the wing, but on the weight of the whole aircraft. So that's what kind of determines how you size the wing. By sizing the wing, I mean not only the skin thickness that you're going to talk about over here, but also the area. And the wingspan to a large extent determines that area. Of course, there's a chord length also, and if it's a tapered wing, it's going to change. But these are things that, depending upon the aspect ratio of the wing, these are things that are going to predominantly determine how heavy an aircraft you can carry, you can support with the lift that the wing can generate. Anybody else? Any questions or doubts? Okay, I guess we'll move on. So, as I said, there were a few questions related to the transverse members. So, let's try to, okay, I just repeated this as homework here for those of you who did not copy already. So, next, let's come to the transverse members over here. Now, the transverse members that you see over here are both in the aerodynamic surfaces like the wing or the tail, as in this particular case, the stabilizers that you have. So you see this particular tail configuration. There can be many tail configurations. One is as a canard, which is in the front, which is not actually a tail, but still performs the same function of stabilizing the aircraft in especially in pitch. And then you have in this case, a conventional rear tail, but you see that it is a high tail. That is basically that horizontal tail is over the vertical tail. So this is one configuration. There can be some configurations where it is below. These are design changes that you will learn as part of your flight and space mechanics course, is out of the purview of the flight vehicle structures. But once that is decided upon as a design decision from an aerodynamics and flight mechanics point of view, in terms of the stability derivatives, etc., then you need to, as a structural engineer, be concerned about where it is mounted, because that will again determine the kind of loads which act not only on the horizontal stabilizer but the vertical stabilizer as well. Now, coming to the horizontal tail over here, you see that if you look at the skeletal structure that you see over here, it consists of the spar, the front spar and the rear spar, and then there are some stringers as well. But the focus in this particular slide is on the ribs that you have over here, right? So that you see over here, this particular cross section, there is a supporting structure, and when you go farther and farther away to the tip of the tail, or even a tip of a wing for that matter, and it could be a vertical tail as well, the tip of the vertical tail. In this case, the tip of the vertical tail, because the horizontal tail is mounted at the tip, will experience substantial loading, but usually the tips are less loaded, and so you would see that the ribs, as you move towards the tip of the wing or tail, would one, of course, because anyway the wing or tail is tapering, so it would reduce in size, but even in terms of its thickness, etc., there can be a reduction, and in terms of the cross-sectional area, amount of cutouts, etc., could also probably increase as you go outboard. Now, you see it a little more clearly in this picture at the bottom over here. You see that you have this structure which is going to be almost the shape of that airfoil cross section, except for certain cutouts which are required for either the control lines to flow or the electrical cables to flow, or some other exchange that is basically happening between the compartments that these create. So the purpose of having them even close to the wingtip, where there is not much of a load, if you're having like an elliptic lift distribution, for example, there's hardly any load which is at the wingtip compared to what, or the horizontal tail tip compared to what it is at the root. But still you would have a rib over there, primarily as a former. We call it as a former because it is giving a form. It is helping the wing or tail retain its shape, the airfoil cross-sectional shape. Otherwise, the shell, thin shell, can undergo large deflections and deformations, because of which the shape can change quite a lot and affect the aerodynamic and the stability behavior. On the other hand, as you move closer to the attachment point to the fuselage, that is the root of the tail or the root of the wing for that matter, you would see much larger configurations for these ribs, because one, of course, the chord has increased in the tapered situation, but more importantly, even the thickness will usually increase because it's going to take much more load at that particular point. So it's not merely a former at those locations, but it is also going to be a load-bearing member, and therefore it needs to have its substantially more thickness over there. So in the fuselage, on the other hand, which is the figure that you see over here, the same what we called as ribs over here, the same transverse members are now given a different name. They're called as either frames or rings, especially in the major portion of the length where the cross-sectional area is very large, or as you go towards the end of the fuselage, either the forward end or the rear end. Especially the rear end, you would have a surface which is not just a frame or a ring, but the entire surface being covered, and that is basically what we call as a bulkhead. We'll see this a little more clearly in the next slide, because what I'm showing here is not the entire fuselage, but just the mid fuselage of a particular aircraft, and with the skin removed, you are just showing that stiffening structure. So you see that there are certain reinforcements which are running along the length, which we call as longerons, and some which are getting cut off because this is, let's say, a door cutout, for example, over here. So the stringer cannot go through that door opening, so it stops over there. So these shorter ones are what we call as the stringers. But now the focus is on the transverse stiffening members, which are, you see, as the frames. Here again, the predominant function would be in terms of providing a shape. So many a times these are called as formers as well. But the ones at the end are going to be of critical nature, the bulkhead, because as you know, in many situations we are going to have an internal pressurization. We'll talk about that in a little more detail in the next couple of slides. So this distinction that you have to understand, that in wings or tails, but basically in any of the aerodynamic surfaces, the same transverse member, almost the similar function that they have, are just given a name, rib. But the same transverse members, when they are in the fuselage, are given a different name, frame or ring, and if they are of much larger cross sections, as bulkheads. But essentially they are performing very, very similar functions. One is to give it an appropriate shape, the other is to transfer the loads. So for example, you would have this is a horizontal tail, but suppose you had a similar cutaway for the wing, you would see that where the engine is attached, that close to the pylons, you would have very large ribs, large in the sense of the thickness or their ability to carry the load, so that there is no concentrated force or coming on or moments coming on the skin, which will not be able to take that. So is this clear? Any questions on the transverse members? Okay, let's move on. So let's look at those in a little more detail for two specific aircraft. In this slide, I'm showing you the British Aerospace 146, which is a high cruise altitude passenger aircraft. In other words, it flies at a relatively higher altitude. In the next slide, we'll look at something which flies at a lower altitude. The difference that comes is because as you go to higher and higher cruise altitudes, you would have the atmospheric pressure being lesser and lesser, and therefore the need for internal pressurization becomes critical. So a higher cruise altitude aircraft, and especially if it's a passenger aircraft, it has to have internal pressurization. It is a must. It is compulsory. So once the internal pressurization is there, there's going to be a lot of hoop stress. So while the skin can take a large portion of that, these frames also help or enable that to happen. So you see that here you have the circular fuselage cross section. The reason why you're going for either entirely circular, as you see in this case, or in many cases you would have circular elements. That is, this portion will be a circle of a certain radius. This portion could be again a circle, but of probably a different radius, but joined to each other. So some kind of a geometry like that, but predominantly you would have either a complete circle or circular elements. The reason is circular elements are best at taking internal pressure. You would have studied cylinders under internal pressure, or even spheres under internal pressure, and you would have seen how the hoop stresses, how the longitudinal stresses. The hoop stress for a cylinder, for example, is almost double that of the longitudinal stress, even from a simple mechanics strength of materials formula. You would see that, of course, changes a little bit depending upon all these stiffening structures and how they actually change depending upon the because you have stiffeners not only in the transverse direction, which you see over here, which are the frames or rings that we talked about in the previous slide, but also the longitudinal stiffeners that you see over here running along the length of the fuselage. Now, there's also a platform over here which separates the region where you have the passengers from the region where you typically put your cargo, etc., apart from many other aircraft systems as well. Now, so this becomes also a floor for the passengers to move around, etc. Now, this is a structure which does not bear too much of the aircraft's loads, but it also is a structure which has to be designed appropriately because the weight of the passengers, the seats, etc., whatever is over there are going to come on this, so that needs to appropriately be designed to take those kinds of bending loads, and the supporting structure of how this is joined to the rest of the aircraft fuselage is also an important thing. You can see there are also truss-like elements that are there in order to help it distribute the load to the fuselage in a much better fashion than in a very concentrated sense. So the whole idea is to have circular elements to reduce the stress levels that are there, and in addition you have these transverse stiffening members which would be further relief. On the other hand, in an aircraft wing, you would have these rib-like structures that we saw in the previous case. So again, this is an Airbus wing. The courtesy for both of these pictures is from the British Aerospace. So here again, you see how they're actually being prepared in a manufacturing assembly line in terms of the shape as well as the cutouts that are there, and the joining points where they need to be joined. In most of the earlier day aircraft, it used to be riveted joints, but as we move more into composites, it's either adhesive joints or co-curing and co-bonding. Any questions on this slide? Okay, let's move on to the next one.
Sir,
Yeah.
this is Vignesh.
Yes, Vignesh.
So, I have heard that during World War II, aluminum was used as mostly as a material of fighter aircrafts. I read about Jiro Hirakoshi from Mitsubishi. When they were making planes, they used to make these riveted joints. So, how would riveted joints fare against this curing currently? The curing process, and what are the pros and cons?
Very good point. See, these joining technologies are very, very critical as each of these component designs, because they are going to be the way in which the load transfer is going to happen between the two components which they join. So when you're comparing, let's say, a co-cured joint with respect to a riveted joint, there are many advantages and disadvantages. One is, of course, you're moving from a metallic structure, which is aluminum alloys predominantly used. We will talk more about some of those alloys in a later class, to a composite. So there is a material change itself. The other important thing is in terms of the load transfer through these joints. The riveted joints, or even for that matter bolted joints, etc., require a hole to be made in both of those structures which are going to be joined. So those holes become regions of potential stress concentration, and can also become regions where a crack can initiate. So that problem is avoided in not only in a co-cured or co-bonded kind of a configuration, but even in adhesive configurations. But they have their own issues. For example, hydrothermal stresses, which are basically stresses which are arising due to the exposure to humidity and or temperature changes. So those can sometimes be critical in a composite aircraft, not only for the composite components, but also a joint, if it is an adhesive joint, or even if it is co-cured or co-bonded, the region where that let's say if this is, let's say this is actually a metallic structure, but let's say this is for just for explanation's sake, assume it to be a composite structure which is co-cured or co-manufactured, which is basically let's say this stiffening structure, which is a ring, along with the fuselage, it's made together. But from a structural point of view, as we visualize, even though it's a single component, we are looking at this as a frame, analyzing it as a frame, and this as a the shell. Now at that interface that is basically there between the ring and the fuselage, even though there are no actual mechanical joints, there is basically a stress transfer which is taking place. The way this behaves under these loads and that behaves under the load is going to be different, but that region is going to be, even if it is co-cured, going to be matrix rich. In other words, there's going to be more of matrix volume fraction compared to the fiber volume fraction. So there are going to be certain issues because matrices are little more prone to hydrothermal degradation, that is degrading in the presence of moisture and temperature, as opposed to the fibers. So you would have certain advantages and disadvantages, but usually the advantages weigh in much more in favor of co-cured, co-bonded structures as opposed to the riveted or mechanical joints in general. Does that answer you?
Yes, sir.
Yeah.
Because I was thinking about the welding techniques as well.
Yes,
like
yes.
People use friction stir welding,
Sure.
something like that, to weld two dissimilar materials at a low, to have a much less voids in the welded regions, or much to reduce. I mean, to have a better welding where the
Right.
crack does not initiate or grow.
Absolutely, yeah. Those are important points as well. Welding is another important joining technology which I forgot to mention. Glad you brought that up. So there is a lot of research going on in welding as well, because we are not completely done away with metals. The metals are still used to a large extent, even in modern aircraft. So metallic joints, not only rivets but also welds, are important, and friction stir welding, as you brought up, is something which is very commonly used in the aerospace industry, and there's a lot of research also still going on, both in the industry as well as academia, in terms of improving these methodologies to reduce the stress concentration levels and make that bond almost as good as a co-cured or co-bonded joint. So research is not only limited to composite materials and structures, but improving the joints as well as even the metals that are involved. Newer and newer alloys are coming up, especially for higher temperature applications, etc., where these polymer matrix composites may not be suitable to handle higher temperatures. You still need to use either a metal matrix composite or a metal itself, or go further to ceramic matrices or carbon matrices, etc. So in all of those cases, the other kinds of materials and their joints technologies need to be continually improved as well.
Thank you for the explanation, sir.
You're most welcome. Yeah. So let's move on to another aircraft. The main difference between the British Aerospace 146 that you saw on the previous slide and the Twin Otter that you are seeing on this slide is one, of course, made in a different continent. From Europe, we are moving to North America. This is in Canada. De Havilland aircraft, which is the source of this particular picture. This is the reason I chose this compared to that is because this is a relatively smaller aircraft. It's still a passenger aircraft, but it is smaller and lighter. So both size and weight matter. So which is again a part of that assignment that you will be doing as a teamwork. You'll see what is the difference between these two. Of course, these two increase simultaneously. The larger the size, usually the larger the weight. But what is the effect of the size? What is the effect of the weight? There are certain subtle differences which I want you to come out with as part of that assignment as well. But let's look at it from a point of view of the cutaway over here, still looking at the skeletal structures. So here you have relatively smaller and lighter aircraft compared to what we saw. So you have much simpler configurations that you see over here. In the case of the wing, for example, you see just two spars. One front spar and one rear spar, whereas in the next picture I will show of a fighter aircraft which is having much larger loading, an attack aircraft, you will see that there are more than two spars. So here two spars are sufficient because it's a smaller aircraft, which means, and because it's lighter, it's going to probably have lesser loads. So you do not want to include too many stiffening structures, which will increase the structural weight and therefore make it less efficient. You see that in terms of the ribs also, they are much thinner ribs that you have over here. Of course, probably this picture and the previous picture are not to the same scale that I have projected over here, but nonetheless, relatively you would see that the rib thickness also is going to be much smaller over here. Then you see also in terms of the stringers also, the number of stringers are much lesser than what you saw in the previous slide, stringers being the longitudinal stiffening members in addition to the spars. And then you have the skin. The skin typically can be also probably a much smaller thickness skin. Again, all of these are things that you're going to infer as part of your assignment as well. So when you see such cutaways, which are very common in the Flight International magazine, you can go to flightglobal.net. You will see many of these cutout structures for both older aircraft as well as newer ones. And you will see that if when you try to look at, they will also number these things and mention what each one of those components are in many of these examples, and then you can try and relate to what you're learning in the class, in terms of what is the function we discussed in the previous class. The main crux of the previous class was in terms of looking at what is the role of the skin, what is the role of the stringer or longeron, and then what is the role of the spar, and eventually the ribs, which we continue talking about today. So when you look at them, you can see where they are located. Are they located at a region where, let's say, the engine is over here? On this side, the engine is not shown, just to give you a better picture of the wing. But basically, you would have a similar engine on this end as well, at the same distance from the fuselage. So at that location, you see the kind of rib configurations that you have. What is it as you go farther away, etc. Sometimes, just to simplify a design or the manufacturing process and the assembly processes, you might have a very similar configuration for all the ribs. So there are many reasons why certain design decisions are basically made, but probably the spacing might reduce as you go to the tip. You might have very similar, because in this case it's not a tapered wing, as you see. It's a chord length, which is basically from the distance from the leading edge to the trailing edge, is the same throughout the span, whether it's at the root of the wing or the tip of the wing. It is identical, which means that the wing is not being tapered like what we saw in the previous example. Same thing if you look at the tail as well, you see a constant chord length throughout. Unlike in one of the examples that I showed in a couple of slides back, where the tail was mounted at the tip of the vertical stabilizer, the horizontal tail, here it is at the root. And again, in terms of the tail, a high tail, for example, will not be in the wake of the wing of the engine. So the engine exhaust that is basically coming, as well as the wake of the wing, those will not be affecting high tail as much as it would be affecting a low tail that you see here. Again, in this case, you're seeing the tail which is on the close to the top of the fuselage. Some cases it could be at the joint at the middle of the fuselage or the bottom of the fuselage. See, many of these design decisions are not made by the structural engineer, but will have implications for the structural engineer in terms of how to do the design, and especially the joint between the wing and the fuselage, between the tail and the horizontal tail and the vertical tail, etc. So these decisions on where to put them will be based on flight and space mechanics, or the what you learn as part of the flight and space mechanics course. In this case, mostly the stability decisions. In this case, also certain stability related decisions, also performance related decisions, most of which are dictated by the aerodynamics of such configurations. So we'll not look at all those details here. Given a particular configuration, how to go about in terms of making the internal structural design decisions is what we will focus on in this particular class. So now we talked about the wing and the tails. Again, in the vertical tail also you see these rib-like structures which are transverse stiffening members. Now the direction is of course different. You do not have the luxury of the symmetry that you have for the horizontal stabilizer and the wing in the case of the vertical stabilizer. In this case, though the wing and the horizontal tail are symmetric and non-tapered. In this case, you see you would have a tapered structure for the vertical tail. Again, all of these decisions are made by the aerodynamicist and the flight mechanics teams. Now, in terms of how you actually populate this internally, in terms of the stringers, in terms of the spars, in terms of the ribs that you have over here, all of these are the structural engineer's prerogatives. Now let's focus on the fuselage over here. this fuselage, it's a smaller and lighter aircraft, and it's also flying at a lower altitude, which means that there is a drop in the atmospheric pressure from the ground, relatively speaking, but it's something that a human body can still manage. So in this case, there's no need for an internal pressurization, which means that you no longer are forced to have a circular fuselage or a fuselage cross section made out of circular elements. You can go for something based on some other consideration. One is, the whole idea of the fuselage is to keep as many passengers there and keep them as comfortable as possible, giving them enough space, or giving them enough room, so to speak. So a rectangular fuselage cross section might be good enough. So if you look at the cross section over here, yes, the edges of that rectangle are kind of curved, but it's not an entire circle that you are seeing over here. It's almost like a rectangular shape that you see, which will make it a little more convenient and comfortable for the passengers to occupy that space, especially because it's a smaller aircraft, and if you make it circular, the person sitting close to the window will probably be banging his head on the walls or even the roof. So you would want to extend the height towards the edges of the fuselage as well. That is basically the left edge and the right edge, and therefore you want to increase the height over there. And so you cannot do that with a circular cross section. You go for a rectangular fuselage cross section to maximize the room over here. Are there any questions on this slide before we move on to the next one? Okay, so
Sir?
yeah.
This is Vignesh again.
Yes,
So
Vignesh.
was this a passenger aircraft, a turboprop?
Yes,
Which was used?
that's correct. Yeah, you're right.
So how many passengers were there?
I'm not really sure about that.
This was a British passenger aircraft.
This is Canadian. The De Havilland company. It's an older. It's an older aircraft. Sorry, I'm not sure about the number of passengers. So you can check on that.
Okay.
Yeah,
okay.
but it's much lesser than the one in the British Aerospace 146 that we saw in the previous slide.
Okay, so it was a turboprop design.
That's
right?
correct. Yeah, you see the engine over here. It's basically a propeller over here. It's which is basically driving the compressor stage. It's basically a turboprop, as opposed to larger aircraft, which will typically have a turbofan. And many of the fighter aircraft will have a turbojet. So these are things that people will study as part of the mechanics and thermodynamics of propulsion course. So we'll not go into too much of detail over there. But whatever it is, it's basically in terms of the thrust that it generates or the power that it generates, and then how that is going to be transmitted where it is joined to the wing. And in the next slide, probably we'll see an engine which is not mounted on the wings, but instead which is mounted on the fuselage, and therefore how it determines the sizing and shaping of the structure over there. So that is what our limited focus will be on in this particular course. But nonetheless, we'll try to visit some of these things where the interfacing is important. Yeah. Now let's look at an attack aircraft. So this is the Harrier. Again, not a very new aircraft, because for many new aircraft, it's very difficult to obtain these cutaways, because people are not willing to share much information. But for older aircraft, usually more and more information starts flowing in as they age. So in this case, you see the Harrier's cutout. So here it is not only it's an attack aircraft, but it is a VSTOL aircraft. VSTOL is an abbreviation which stands for vertical or short takeoff and landing. So unlike most aircraft which need a runway and therefore a certain takeoff length in order to take off, if you need to operate from regions which cannot afford a large runway, which is the case for many locations from which fighter aircraft are typically operating from, you need to have aircraft which can have thrust vectoring, either through tilting their wings or tilting their engines or some other technologies, and so that they have thrust vectoring basically coming in. That is, in other words, your thrust can be vectored or change its direction. Not only its the value of the thrust, but also the direction of the thrust relative to the rest of the aircraft. And that change that you're going to basically see is going to help you in either taking off or landing, or both, in a vertical sense, which is the ideal, but in some cases maybe a short takeoff or a short landing length of the runway, so that you can operate from much more smaller airfields than what you would, or even take off and land from a non-airfield, let's say just on the road or something like that, under certain emergency situations. So the fact that it is such an aircraft means that the loading is going to be very large. An attack aircraft is going to be involved in a lot of maneuvers, and these maneuvers will make it important for it to be able to manage larger load factors. In other words, its lift, unlike in a cruising aircraft where the lift is equal to the weight of the aircraft, here the lift can be many times the weight of the aircraft, and it can sometimes be negative also. So it's in the opposite direction, that is. So in all of those cases, you're going to have much severe loading situations occurring, especially on the wing and also the tails, which are the ones which are housing the control surfaces and helping with these maneuvers. So these wings and the tails, you will see, compared to the previous two pictures, are having many more number of spars. In the previous slide, for example, the smaller aircraft, we just saw 2 spars. In the one before that, we saw probably 3 spars. Now you see many more spars. In other words, you're creating many more wing boxes to take torsion, and the spars to be able to handle much larger bending moments that are going to come from a larger lift distribution, and therefore a larger drag distribution as well. Then again, the ribs, because you want that shape to remain, and also you want the many more attachments. Not only do you have engines, but in this case you have a lot of ammunition that is coming over here, the armaments that are going to be released from this. Even initially they are all joined to the wing, they are mounted on the wing rather, and so you would have the need for the wing to be able to take their weights, so you need to design the transverse stiffening structures to be able to transfer that load which is coming from these armaments onto the wing structure. So all of that has to be taken into account as well. So the skeletal structure that you see for the wing as well as the tails are going to be much more complicated. But despite this, all of this complexity, in terms of the functional roles that each one of these is going, what role does the spar have, what role does the rib have, what role does the skin have, what role do the stringers have, all of these are going to be one and the same, what we discussed in the previous class and what we discussed for the previous 2 examples, just that it's just scaled up in sizes and the amount of load that it is taking. Still, if it is made out of the same or similar material, then you would have to have the same levels of stresses that it can go to, just that you would have probably a thicker skin, more number of spars sharing the load, and therefore still under the same levels of stresses, and therefore not failing. So this picture of the Harrier, the Cutaways, courtesy of Pilot Press Limited, and here you also observe the rib geometry in the wing changing from the root to a tip. So this is what I mentioned in a previous example also, that at the tip the load is very less, almost close to 0, and therefore the only reason why you have a rib over there is to have it as a former, basically to give it a form or a shape. Whereas as you go closer to the point of attachment of the wing with the fuselage, you would see not only is there the fuselage as huge stiffeners in the transverse direction, which could be bulkheads or much larger frames or rings, you would have have in this case the rib also coming from the wing at the root, being much larger dimensions, especially in the thickness direction. So that's as far as that is concerned. In addition to the concentrated loads coming from the engine and the armaments, you can have concentrated loads coming from the landing gear, especially when it's in the takeoff or the landing configurations, and also when it is taxiing on the runway. So those concentrated loads which are coming, so this is the landing gear structure that you have, where it is joined to the fuselage, and this these landing gears you see one over here, this is basically attached to the wing. So the load has to be transferred from the ground through the landing gear to the point of attachment to the wing, or the point of attachment to the fuselage, and all of those are typically concentrated loads, or loads which are distributed over a very small surface area, and so you need stiffening structures in order to handle those as well. Stiffening both in the transverse direction as well as the longitudinal directions to appropriately distribute that stress to the skin. So mostly it is the aerodynamic loads on the skin which is being transmitted to this, but here these are typically attached directly to those frame structures, so that the transfer of load is not first to the receiving end is not the skin, but the stiffening structure itself, because these are relatively more concentrated or distributed over smaller surface areas compared to the aerodynamic loads of lift and drag. Are there any questions on this? Okay, let's move on. So now let's talk about the history of how these structures have evolved over a century. You still have the same scary skeletal structures over a century. We talk about a horror movie called saal baad. Saal baad also, these look fairly scary. Even more scary because now we are expected, or our structures that we design are expected to carry more with less. What does that mean? That is, you have even more heavier aircraft, larger aircraft today compared to previously about a century back. But now you are expected to do that with much lesser structural weight percentages. So the amount of allowance that the aircraft designer used to give for the structural material was much more earlier in terms of a percentage of the total maximum takeoff weight of the aircraft. But now they are expecting us to do that with much lesser percentages, because they want to give the rest to the fuel to increase the range, for example, or to the payload, so that they can carry many more passengers or much more cargo, or more allowance of the cabin baggage and the checked-in baggage per passenger, etc., or to fly at faster speeds, or combinations of all of these performance improvements. Or in the case of fighter aircraft, let's say, to be able to perform many more maneuvers, you want a lighter aircraft, and one place where they try to do that is try to see how we can minimize the structural weight, which is basically the empty weight of the structure, the load-bearing components of that. So in other words, the requirements are becoming more and more challenging, but we are up to that challenge, because challenge is what makes our job much more interesting, because we are innovating not only with newer materials, newer joining technologies, but also newer geometries. See, a structural engineer is not all about materials and materials alone. There's a lot to do with materials, but there's equally lot to do with the geometry as well. Though the overall geometry, as I keep repeating, is dictated by the aerodynamicist or the flight mechanics teams, still the internal geometry is entirely our freedom in terms of how we design. So even with the same materials, we can do a much better job if we pay enough attention to the geometry of the design. And this is something we learn from nature as well. Nature, the way it has shaped various structures, not only in our skeleton, but also if you look at various other animals, vertebrates in particular, you see the kind of skeletal structures they have, very different for a bird as opposed to for a let's say a creature on the land, let's say a tiger, because one is supposed to fly. On the other hand, how is it for, let's say, a mammal which is supposed to swim, let's say a whale, for example. So the kind of structural differences depending upon the kind of mobility that they need to have is quite different for each one of these cases, and that's something that we need to explore as well. So just to give you an idea of the numbers that are involved, the wing loading, which means that the total weight of the aircraft is actually handled predominantly by the wing. Yes, the horizontal tail generates a little bit of lift. Maybe sometimes it's a negative lift also, depending upon the angle of attack that it is exposed to in a particular flight regime. But almost the entire weight of the aircraft has to be carried by the wing. So the wing loading becomes a very important parameter, by which we mean the total weight of the aircraft divided by the planform area of the wing. So in other words, if you look at it from the top view, what is the area of that wing? Okay, for let's say the simple case of the untapered wing that we saw for one of the aircrafts earlier, the smaller aircraft, you would see that the chord is the same throughout. So it's a rectangular planform. So the planform area just becomes the chord into the span. Span being the distance from the left end to the right end, the one tip of the wing to the other tip, multiplied by the chord length, which is a constant for that particular aircraft. So that becomes the wing planform area. For a tapered aircraft, it's a trapezoid that you have to measure the area of, the top area of. So whatever that is, so if you divide the total maximum takeoff weight divided by the wing area, you get a parameter called the wing loading, which is a very, very important critical parameter from many different points of view, especially for the structural engineer, but also you will see from a design engineer point of view, or even aerodynamicist point of view, etc. So this helps not only a structural engineer decide on the materials and the sizing of the components, but also in terms of the aerodynamicist, in terms of arriving at different planform configurations, different airfoil configurations, etc. So this is something that is a primary deciding factor for many decisions that are supposed to be made in terms of the overall aircraft design. Now, this particular quantity has become 13 times over a century. Let's start from about, let's say 1916, 1917 to about 2016, 2017. Over this century, of course, there's a wide variation from aircraft to aircraft. We're talking about most of the aircraft, leaving out a few outliers. The average wing loading has increased 13 times. Would you believe it? Which means that we are expected to take the same weight with a planform area of the wing, which is 13 times smaller. Or with the same planforms areas that were there earlier, we are now expected to take an aircraft which is 13 times heavier. So this is the kind of challenge that has been thrown to us over a century, and luckily we have been able to meet that. And this is not the only thing. The other thing is that they want us to reduce the structural weight percentage. So that has drastically come down over the same period from 1916 to about 2016, from an allowance that we structural engineers used to get. They used to say if the weight of the aircraft is, let's say, 100 tons, you can take about 40 tons for this. But no longer the case. We are not allowed that luxury of using 30 to 40% of the total maximum takeoff weight as just these structural components of skin, stringers, spars, ribs, and the bulkheads, etc. But now we are expected to do that with just about a quarter of the weight, or even lesser, and this trend is going further down, might become 1/5 or 20%, probably already is for some aircraft, but that is what we are trying to do. So this is what I mean by with less. So with lesser amount of structural mass, you are expected to do much more than what you were supposed to do about a century back. Fair enough, because that's how technology moves. Now, in terms of, and you see this in all other technological areas as well, the kind of computational speeds that have moved up in terms of the miniaturization of computers, all the way to the mobile phones, which are probably much more powerful today than many of the supercomputers in the earlier days, and still much smaller. And all of this has been possible, one, because of the materials research. And a lot of this materials research is out of the prerogative of conventional structural engineers. But these days, there's been a lot of interaction between material scientists and structural engineers to understand each other as bodies of knowledge, so that we can design materials, new materials upfront, both metals as well as composites, to be able to handle this kind of challenge in terms of the performance as well as the allowance required to enable that performance. So there is a pull from both of these directions, and we are able to handle that primarily because of the material evolution. The other is because of the joining technologies, and the third most important is also the geometry configurations that we are able to go for. First improvement in this whole thing was going from a monocoque to a semi-monocoque. That in itself helped us to bring this percentage down quite a lot. Otherwise, you would have had to have much thicker shells to deal with, which are very heavy. Now you can do with thinner shells and distribute the rest, smaller percentage that we have now towards all of those stiffening elements. So this evolution is something which has happened over a century and is a continuing process. And we earlier talked about biological systems that we need to learn of. They evolved over millennia. So no wonder that they are doing so well. But these aerospace technologies have improved just over a century, or a little more than a century. And even from all the learning that we have got from automobiles, etc., and other machinery, etc., you even look at the Industrial Revolution, it's just a few centuries over which many of these engineering structures have improved, and we have done fairly well considering the much shorter time period that we have. But that's been primarily possible because we have been learning from nature. These biomimetics, rather than, we are not copying what is there in the nature, but we are trying to adapt the understanding that we get from there in terms of improvising on our own engineering designs. So this is in terms of that expressed in a pictorial sense. If you look at this black 3D cube that you have, or cuboid that you have over here, in 1917, the wing loading, which is the total weight divided of the aircraft, not of just the wing, divided by the wing surface area, in 1917 was of the order of 350. Again, there would have been very lot of variations from aircraft to aircraft, but we're talking of a ballpark value just to get an order of magnitude understanding of what it was then. Whereas in 2016, it from 350, it's become 4,800 Newton per meter squared. So this is approximately 13 times that I was talking about. On the other hand, the amount of the total weight which is allowed for the structure to take was about 35%, which is the average of 30 to 40% over there, and it has now become almost as low as 22%, and even further reducing, because this figure is from 2016. Composites especially have been doing a remarkable job in bringing this down further, and of course co-curing, co-bonding, which are reducing the stress concentrations at the joints, which used to be the critical design regions in terms of sizing in many situations. That's coming down as well. So you can see a trend more towards 1/5 of the weight being structure as we go forward. Are there any questions on this before we move on? Okay, so in your assignment, you can also, if necessary, talk about, because anyway you're talking about getting the data for the wing, the total weight of the aircraft and the wing area. So you can also look at in terms of the wing loading, that is basically the weight divided by the area, and see if you can get some of the inferences based on this wing loading, rather than just the wing weight or just the span which goes into making this wing area possible. Because because this wing area in a rectangular case, S is equal to just B, which is the span, into C, the chord. But some kind of a trapezoidal thing, if C changes from C root to C tip, which is the chord, which is the root chord to the tip chord. So you'll have to appropriately take the average of that and multiply by the span in order to get that wing area over there. So now that you know this particular quantities of significance here, the total weight of the aircraft divided by the wing planform area in Newton per meter squared, you can see how this kind of dictates those clusters as well. So if there are no further questions, I'll move on to the next slide. Now the load-based component classification, and it's basically to understand this that I had given a preview in terms of that quick quiz that I put up. And thanks to many of you who very quickly responded to that. We will see the results of that in the next slide. But before that, I'll just tell you the reason why I gave you that particular question. Before that, probably let's take advantage of these two pictures over here. So we already talked about the aerodynamic surfaces and the main fuselage. But now suppose we come to the other end. We also talked about the empennage, which is basically the rear end of the fuselage, along with the two stabilizers. Now let's come to the region beyond the cockpit, which is typically called as the nose cone of the fuselage, because it's at the nose of the fuselage and it's usually a conical shape that you have over there. Here you could have a cylindrical shape. You have having a ending it with a conical shape, very similar to the empennage as well. And again, we are looking at the skeletal stiffening structure with the skin of that removed for a particular aircraft. And you see, once again, you have longitudinal stiffening members. You have certain cutouts for something which has to go in or out over there, or certain cables, etc., coming in and out. Then it doesn't end in a tip, but it ends with a bulkhead that you see over here, which is basically nothing but a transverse stiffening member, but almost entirely covered, rather than just as a frame that you see with holes, cutouts over here that you see over here. These are also transverse stiffeners. This is also a transverse stiffener. This is just a frame, whereas frame or a ring or even a former, whereas this is basically a bulkhead. Now, the reason why these are important is because you have the internal pressurization load creating not only a hoop stress, which is the dominant stress, but also a non-negligible longitudinal stress, and to a large extent those are taken by these bulkheads as well, apart from the load transfers that they have to do between the various components which are joined to it, like the stringers and the skin. So now let's come to a much more generic topic, that is the load-based component classification from a structural engineer's point of view. Something like the stringer that you see here is just a bar or a column. We call it a bar typically when it is under tension, and we call it a column if it is under compression. So in the case of let's say the fuselage, if the dominant load, let's say, is the self weight of the fuselage, then you are basically going to have the top ribs under tension and the bottom ribs under compression. Let's say this is on the ground, it's not internally pressurized, and then it's the self weight is the main load that is coming over there. So this is trying to bend downwards. In other words, the nose of the aircraft is trying to go down because of the self weight of the fuselage. So the top stringers are going to be under tension. You call them as a bar. The bottom stringers are going to be under compression. You call that as a column. And because these cross-sectional dimensions are small compared to their lengths, 1D approximation can be good enough at many times. We'll see what we mean by good enough and how can they be made good enough later on, because any structure, be it this stringer or these transverse stiffeners or the skin, they're all in reality 3D structures. from a modeling perspective, can we treat it as a lower dimensional structure and still get reasonably good results, is the question. And yes, the answer is yes. For most structures we can do that and still get reasonably good results, and that is what we will focus on for almost the entire course. So understanding these terminology from a structural engineer point of view. Earlier we were talking from an aerospace engineer point of view. This is called a stringer. Something else is called a spar. But both from a structural engineer point of view is just a beam, right? So now, or a bar, depending upon what kind of loads that they are taking. So from that point of view, the dominant load either for a bar or a column is an axial force. That is a force along the length or the longitudinal direction of those structures, which could be either tension or compression, and correspondingly you have these two different names. But essentially it's a one-dimensional structure. The second kind of structure that we'll talk about is a shaft. And again, in all of these cases, being from a flight vehicle structures perspective, these are not going to be solid. In most of the automobiles, for example, you could have a solid shaft, but here you have thin-walled shafts. In other words, it's going to be a hollow cylindrical configuration, or sometimes not even a cylindrical configuration. The box beams that we saw in the wing, for example, made from the skin of the wing and the web of the spars, the front spar, rear spar, and the bottom skin and the top skin of the wing. That's a box beam. That's not circular, but it's almost rectangular, but once again thin-walled and hollow. So all of these elements which are going to take a torque are typically again going to be fairly long structures, and they're going to be of cross-sectional dimensions which are much smaller compared to the longitudinal dimension. Transverse dimension being much smaller compared to the longitudinal dimension once again makes them suitable for a 1D approximation. But now, even though they are both essentially 1D structures, one is called bar or column because the dominant load is an axial force. Here the dominant load is a torque, and therefore we call it a shaft. But in reality, they can, of course, they are both 3D, and also they will be taking a combination of these. So you can't either call it a bar or column or a shaft. You have to call it a 1D structure, which we will generalize it to be a beam going forward later in the course. But right now, these differences are essential to understand if you want to treat each one of these individually, and it's still in the linear regime when you can treat them individually and then add them up using the principle of superposition, which will work for very small loading situations, or if the structure is not too thin, for relatively thicker structures. But essentially most flight vehicle structures will be thin, and therefore it's essential to work with all of these loads up front. The third kind that we have is the bending moment. And when there is bending moment, especially let's say in the spars or in the stringers, etc., and then you have once again the length of the spar or a stringer much larger compared to its cross-sectional dimension, and now the same thing acts as a beam. But once again, because of that difference in orders of magnitude of the dimension, you can probably treat it as a one-dimensional structure with reasonably accurate results. But if you were to treat all of these as three-dimensional structures, you'd get even more accuracy. Just that it would take much more computational effort to do that. So and since the accuracy is not going to drop too much, if you can deal with this as a 1D structure, you can enhance the computational efficiency. And that's why the need for what we call as a dimensional reduction from 3D to 1D in these cases. Another dimensional reduction is from 3D to 2D, where in the case of the wing skin or the fuselage skin, which is basically a thin shell, or in certain regions which are flatter, it could just be a plate. But essentially it's a panel or a combination of panels which are joined to each other, which is basically your two-dimensional structure. So that's basically something which can handle shear forces or shear force distributions. So in the skin, for example, it's not only the pressure load which is coming from the top, which essentially most of it transmits to the underlying skeletal structure of the let's say the stringers and spars, the spar cap in particular. But it also takes a little bit of bending, but that's not the main purpose of the skin. We saw three different purposes, but from a structural point of view, the main load that it takes is the shear force or the shear force distribution. One is the shear force coming because of the viscosity of the air, which is acting on the top. But even more importantly, it's the transverse shear. Because of the lift distribution, you're going to have transverse forces on this cantilever beam, and that transverse force is going to cause shearing stresses on the skin, especially from the drag for the cover skin and from the lift for the spar webs. Now, all of that shear force is very efficiently taken by a 2D structure. Why do we call it a 2D structure? Because any panel or shell or plate is called so because its thickness is very small compared to its other two dimensions. So now the transverse direction becomes the thickness direction. It's always this smaller direction we call as this transverse direction. In these cases, it was the cross-sectional dimension which was transverse, and along their length we call it longitudinal direction. Now, for a panel, you have two directions in which it is large. Let's say the slide, for example, this is the height of the slide and this is the width of the slide. These two are larger dimensions compared to the thickness of the slide, which is almost zero, right? So now that thickness direction becomes the transverse direction. So in that transverse direction, there are transverse shear stresses, and which are counteracted by the transverse shear strains. So these are efficiently taken there, and we call them 2D because two dimensions are large enough to be considered. The other dimension is too small, and it has to be appropriately dimensionally reduced from 3D to 2D in order to still have the same, almost same accuracy as the 3D model. So these are the four kinds that you have, and now there is a need, as I said, to improve the computational efficiency to model these actual 3D structures as either 1D in the case of the bar, column, shaft and beam, or as 2D in the case of the panel, shell or plate. So we have to engage in a process called dimensional reduction. It might sound like a big name, but this is essentially what you have done as part of your strength of materials as well, where you derived a beam theory, where you derived the torsional theory, etc. In your strength of materials classes. Without being told that you're actually doing a dimensional reduction, you are doing that. But those kinds of textbook like formula that you came up with there are not good enough because they had certain ad hoc assumptions which were valid in certain special cases but were not in most generic cases, especially in thin-walled kind of configurations that we deal with in aerospace, as well as the kind of factors of safety that we have here compared to typical machinery or automobile structures. So therefore, this dimensional reduction is a very important process that we need to give a lot of thought to, how we are going from 3D to the 1D or 2D model. 1D in these three cases and 2D in this case. How we are going that. When you're going from 3D to 1D, you're actually having two dimensions which you're reducing. So these derivations are much more complicated compared to this derivation. But once you derive, handling this is much easier because now you deal with only one spatial dimension, whereas here handling this is much more difficult because you still have two dimensions to deal with. So in terms of deriving a 1D theory, it's much more difficult compared to deriving a 2D theory. But employing a 1D theory is much easier compared to employing a 2D theory. But in very rare cases, you would have the same theory which is applicable for 3D, applicable for both 1D and 2D. Can anyone think of an example of such a situation? Yes, you can think of examples where 3D can be dealt with as 1D and some other examples where 3D can be dealt with as 2D. But can you think of any example where a structure can be dealt with as 3D, 2D as well as 1D, all three possibilities. Any geometries that you can think of? Anybody can answer that? Just recollect what we explained in terms of when we call it a 1D structure, when the longitudinal dimension is very large compared to the other two dimensions. And when do we say it is 2D? When the thickness direction is very small compared to the other two directions. Is there a geometry that you can think of which satisfies both these? Anybody there?
Sir, rudder.
Rudder, good. Yeah. Anybody else? Any other? I'm not. Don't talk about it from a point of view of the aircraft. We'll talk about that later. We'll see examples of that later. But even if you're non-aerospace engineer, purely from a structural point of view, either as a bar, column, shaft, beam, panel, some other term that probably can be, of course it is 3D, everything is 3D, but can be dealt with both as 1D as well as 2D.
Maybe tube, sir.
Tube? Did you say that?
Yes, sir.
Yeah, okay.
Tubes.
Okay. Good. Because if you think of the tube, let us say, of course it is very clear to see why it is 1D. You can think out of it as a 2D because it's basically a shell wrapped around itself. So if you're able to give an axisymmetric boundary condition or something that boundary condition which repeats and says that as you go around this shell and come back to a particular length of the shell, which is 2 pi r, then you're basically saying that the displacement should match, the stresses should match, etc. So instead of giving for a shell which is open and therefore giving a free or a loading boundary condition at these edges, now you're changing that boundary condition to that. So that's a very good example of a situation where it's actually a sheet which is now made into a tube, a long tube, and therefore the tube can either be dealt with as a one-dimensional structure, this being the x direction being the only direction of relevance, or it can be dealt with as x and let's say y along the circumference. Now if you're thinking of it as a shell, right? So that's a good example. Any other examples that you can think of where you have a rudder was a good example too, because basically you're thinking of the length of the rudder large compared to its chord or the thickness of the airfoil which is used to make the rudder. But then in terms of so therefore you can deal with it as a 1D. But again, in terms of the same cylinder example, if you're unwrapping it, you're basically looking at it basically as a shell with which, but there's a one more, without even unwrapping it or giving these kind of axisymmetric boundary condition, an example where you can deal with something as both 2D and 1D.
Transmission shaft?
Yes. Yeah, so again that comes under shaft. So a transmission shaft which is thin walled, fine, fair enough. Anything else that you can think of?
The shear wall.
Yeah, shear wall.
Shear wall.
Okay, good. Yeah, shear walls. For example, if you're talking of the let's say the spar web, it is something that can, which is very long, running along the span of the wing, but its width is small compared to the length, but the width is also large compared to the thickness. So now you have two levels. One, so basically all structures will have three dimensions because we are talking of 3D structures, but all that we are saying is that in a 1D structure, one dimension dominates compared to the other two. In the other case, the panel case, one dimension is being dominated by the other two, right? Now, if you have two levels of changes, that is, one dimension is very large compared to this dimension, but this dimension is also very large compared to this dimension, then you have two levels of dimensional reduction possible. You can go from 3D to 2D. Your accuracy will suffer a little bit, but computational efficiency will increase. Again, you can go from a 2D model to a 1D model, where once again accuracy will drop a little bit, but efficiency will improve further. So all the examples that you gave are great examples. Another example is thin rectangular strip. If you just have a thin rectangular strip, like let's say a scale, a ruler that you use to draw straight lines, that is basically having a length which is very large compared to the width, and the width is very large compared to the thickness of the scale or ruler, right? Now that is can be dealt with as of course as a 3D structure, can be dealt with as a 1D structure like a beam, can also be dealt with as a plate. Okay, so there are situations like that, and one common example of that application is in helicopter rotor blades. So helicopter rotor blades have a inner structure called a flex beam, which is a skeletal structure, and that skeletal structure is usually a thin strip that you have, and that thin strip is able to be modeled as a 3D, as a 2D, as well as a 1D. But basically anything where you have this dimensional reduction dropping in two levels rather than in one level, then you basically have a kind of structure which can be dealt with both through two different kinds of dimensionally reduced models, that is 2D and 1D. Okay. So now the dimensional reduction to a 1D results in what is called as a generalized beam, because we're going to call all of these as beams. Even though they can be bar, column, shaft, whatever, we're going to call that as a generalized beam. Okay. And in general, they can be initially curved and twisted. In other words, your beam under the absence of any load need not be straight. It can already be a curved beam. Example of that is a frame. A frame structure is having certain curvatures, but basically those can be dealt with usually as two beams which are joined to each other, or two bars which are joined to each other. But now we are talking of everything as a beam, and these beams in general need not be straight in the undeformed configuration. Even when the no loads are acting, it can be a curved beam, right? And it can be a pre-twisted beam. In other words, the cross section is having a certain angle of twist at the tip relative to what angle it is at the root. So now this kind of change is called a pre-twisted or initially twisted beam. And this is very common. If you are looking at the aircraft wing, you would have a wash in or a wash out of the aircraft. You'll study these terminology in flight and space mechanics course. But basically what you're essentially saying is that the angle of attack of the tip and the angle of attack of the root are going to be different from each other, even in the same phase of flight, because the aircraft wing is manufactured in such a way that there is a certain angle over there for various reasons. It could be either a washout or a wash in, right? Now so that's an example. And helicopter rotor blades almost always will have a pre-twist in them. Okay, so now these two configurations are examples of initially twisted beams, and you can have initially curved beams as well. They're very rare examples, but a lot of aircraft design is moving towards that arena. And finally, we're talking of 2D generalized shells. So now 2D generalized shells are basically your panels, and also in some examples, as I said, the rotor blade, the shaft that you're talking about, etc., where you can probably, for improved accuracy, improved over a 1D model, but still reduced compared to a 3D model, you can probably deal with some of them as shell models as well. It's kind of a compromise between 3D and 1D where it is applicable. It's not always possible for a beam to be modeled as a shell as well. Okay, so where it is possible, if you want better accuracy, you go for a shell model. If you want better computational efficiency, you go for a beam model. So either case, because we are moving away from 3D to a lesser D, 1D or 2D, the efficiency in terms of computations is going to be enhanced, In other words, you're going to speed up your computations, you're going to use lesser computational resources, or with the same computational resources, you're going to consume lesser of CPU times, and probably even the memory involved as well, etc., because the number of degrees of freedom, etc., when you're going to a numerically discretized model is going to come down drastically. And at the same time, there is a small drop in accuracy. If you do the dimensional reduction properly, and that properly is within quotes, technically what it means, mathematically what it means, from a physics perspective, science perspective, what it means is what we will see as we go forward in the class. But if we do it properly, that drop in accuracy would be almost negligible. But the efficiency gain would be CPU times dropping by, let's say, 10 times in the case of a panel to almost 100 times in the case of a 1D structure like this, whereas the accuracy might drop by 1 or 2%, so which we can actually live with. But the efficiency increase is so much that we cannot afford to go with 3D models in many situations, especially when you're dealing with larger structures like the entire aircraft wing or the entire aircraft. You cannot deal with everything as 3D. You will have to include 2D or 1D elements and interface them with the 3D appropriately in order to do this. So with this, I think I overshot a little bit as usual, so I will stop. I actually wanted to bring in this context the poll that we had, the quick quiz that we had. So I will do that in the beginning of the next class, and then we will take it forward from there. Are there any questions, doubts, or any clarifications needed on what we discussed today?
Sir?
Yes.
In the assignment problems, in third question,
Yeah.
you told us to draw a plot, make a plot between skin thickness and gross weight.
Yeah.
But we know that skin thickness varies continuously,
Correct. Yeah.
along the length of this
Correct.
span.
Yeah.
So, which thickness we need to consider?
Some average thickness. Like for example, in this slide that I showed you, see here, I'm having 30 to 40% range, but I'm just showing you 35% over here, right? Similarly, I have 22 to 25%, but I'm showing you the current state of the art in terms of 22%, okay? So just, so you will have a range for many of these quantities, but just choose one of them either in the mid-range or one extreme, and just mention that. So that's good enough, okay? Because as I said, we are not actually so much interested in the absolute values there. We are more interested in the trends that are happening. What is kind of change that is happening? So when you have, you will definitely have a larger thickness of the cover skin closer to the root where the stresses are large compared to what it is at the tip. So for example, if you have both of these data for a particular aircraft, take the root skin thickness, because that is what is from a structural point of view much more demanding, right? So, but if you don't have or have it somewhere in between, that's fine too. Just take and mention that that's what that thickness is. So for each one of those data points, do mention if you have information on where that for which location of the wing it is from, mention that. Or if you have location for multiple locations, some kind of an averaging that you have done, how you have gone about doing that averaging, mention all of that when you're explaining the inference, explaining the takeaways from the plots that you give, right?
Okay, sir.
Yeah. Any other questions? Okay, then otherwise I'll stop sharing and we go back to this. I just wanted to see you still have 42 participants. That's good. So I think this is a right time to probably take a together mode. So can you all switch on your video cameras if you have it, and click on the ellipses, that is the 3 dots on the top, and go to the together mode so that we can visualize all of us together. We'll take a picture with our whole class. Good to see 42 people, I think, which is the total strength of this class. So somebody is wearing a mask as well. You around people, Vignesh?
Yeah, we don't want the virus to get through.
So especially in the together mode. That's one highly responsible person. Yeah. Okay, I still don't see 40 people here unless I'm not counting properly.
Only one person is shaking. Now it's
Okay, I guess I'll take a screenshot now. Yeah, I think adjust yourself coming forward or backward so that we all look at the same size. Otherwise, some of us look much fatter than others. So, as if you're relaxing on that chair so that you're not too close to the camera, in which case you look like me now, and only your face is there. So that we have some kind of scaling which is done between all of us. Right? Okay. Yes. Okay then, smile. Yeah, feel free to make any gestures that you want to. It's a fun picture. Let's take one more.
Yeah, Modi is also with us.
All inclusive. Okay, good. Thank you. So that I'll stop the recording.
Hello?
Yes?
Sir?
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्यो मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा